Hello, my name is Tushar and welcome to my YouTube channel. Today I'm going to cover a very basic algorithm for machine learning and AI. For any math student, this is a very important algorithm which is named as gradient descent. We'll be covering the theory part as well as the practical part while we'll be coding the same algorithm from scratch in Python. So if you are someone who is just getting started with machine learning and AI, it is a very important topic for you. It is very it is the heart of machine learning. So let's get started. Uh, I'll be explaining the whole algorithm in terms of mathematics first of all, and then we'll code it up in scratch in Python, from scratch in Python. All right. So let's say you have a mathematical function fx. It can be anything. It can be x square or x cube plus 3, any function of x. Let's say, all right. Let's say graphically, for example, we can say, let's say this is fx. We are just assuming, all right. So if someone asks you like at which x fx is minimum, let's say we want to find a x naught for which fx is minimum. By looking at the graph, what will be the first thing coming to your mind? At which x fx is minimum? At this point, right? This is the point where fx is minimum, right? Apart from this, if you go leftwards, the value of f increases. If you go rightwards, the value of f again increases, right? So this is the point x naught we are interested in, right? By looking at the graph, this is a easy thing to convey, right? Anyone can look at the graph and say that at this particular x naught, the fx is minimum and this is the value, right? But how to do it programmatically? Gradient descent is the algorithm which does the same. How to do it programmatically? There are two ways. Uh, there are two ways. Let me make a distinction. The first way, which is a direct way, and second way, which is an iterative way. Let me write it down here. A direct way where we can find this x naught directly in one shot, and another way which is iterative way, in which we have to take some iterations to come up this point x naught. We'll be starting with some random x and we'll be approaching toward x naught. This random x can be anything. Let me explain you. The direct way is if you had a maths in your high school, you must be aware of how to find the local minima and local maxima. This is the same thing, right? This is the local minima, or we can say the global minima, right? For this particular function. The direct way is something same. What the direct way says, just take the derivative of x with respect to x, make it 0 and find x naught. For example, let's say the function is x square, all right, and we want to find a point where this function is minimum. So what we'll do, we'll take the first derivative of f, df by dx, which will be equal to 2x. We'll equate it to 0 and will find x. This way x will be 0. So this is the point at which the minima is, because if you'll draw the graph of x square, it will look something like this. At this point the gradient is 0, gradient, or let's say the derivative is 0. This term is 0 at this point, and this is the point where this function becomes minimum, right? This is a direct approach, right? Just compute up the derivative of the function whose value you want to minimize, which in this case is equal to f. Just find the first derivative, equate it to 0, and find x. At this point the whole function's value will be minimum, right? So this is a direct way, and there is another way as well, guys, which is iterative way, which is not the direct way, which is iterative way, in which we have to take certain iterations. We have to recompute x. What we will do in this case, we'll start with a random x, let's say x dash, which is random. We'll choose randomly any x. Let's say this is the function, and this is the value of x, the domain of function, basically the value of possible x which can go inside this function. From that domain of the function, we'll pick up any random x, anything, right? It can be anything. And using that random x, like let me write the pseudo algorithm to find it in iterative way, like while basically the check to find if we have reached that value x, or at which the fx is minimum, the check is same, that the derivative of this function, let's say f naught y, let me erase it up, the value of this modulus must be very close to 0. The condition is will be this one at x dash. Like if this is not true, we'll keep on iterating, and what we will be doing is we'll be keep on updating x dash with this particular value, x dash minus alpha time df by dx at x is equals to x dash. So it is simple, guys. We will choose a random x, anything from the domain. We'll compute what is the value of first derivative of the function whose value we want to minimize. We'll find that value, and if it is not close to 0, and this can be anything like 0.001, or this is based on your assumption. Like you can set it, if you want very accurate result, you can set it to very close to 0 or equal to 0 as well. But if you are satisfied with let's say you are satisfied if the function, if the algorithm return you this value instead of this value, like in this case, if instead of 0 you are satisfied with let's say 0.001, because at that value as well the value of the derivative will be close to 0, you can set it as per your need in that case. So the thing is, if we will keep on iterating in this way, like we pick up the random value of x from the domain, we find compute the derivative of the function at that particular value of x, and if it is not close to 0, we'll keep on repeating this particular thing. We'll keep on updating x. Basically we find x dash using this value. Alpha is actually is something which we call as learning rate, and this is something which is close to 0, again something like 0.001 or anything, a small value basically. And this is the derivative of this function. And why this algorithm works, guys? So now let's talk about that, why this works. Let's say, like, first let's try to understand what the derivative of a function means. Let's say df by dx is something. What is df by dx? Basically, this is change in f. Like, what does this tell us? Like, let's say we have a function which is something like this value of x, this is fx. We take some random x, let's say this one, and if x increases, let's say we change it to this particular, this much of difference. We started from here, we move here, this is x1, this is x2, let's say, and the value of function here, some value was there, let's say f1, and again here is some value, let's say f2. Now the change in x is represented by dx, let's say delta x, which is delta x, let's say x2 minus x1. It can be positive, it can be negative. If you increase the value of x, if x2 is greater than x1, the delta x will be positive, otherwise negative. And delta f, the change in value of the function which comes in return. Let's say you change the x, the function will actually change, right? What is the change in f? f2 minus f1. Now derivative of a function is actually the ratio of change in f to change in x, right? This is the derivative of a function, which is actually df by dx. df by dx comes up when change in basically small d represent a very small change. Small d says that we have tweaked the x by a very small amount, and there will be resulting change in f, which is df in this case. Like in the macro scale, this is that the micro scale, that the macro scale we can say it is delta f by delta x. So what if it is greater than 0? What does it say? It say that if x increases, if x2 is greater than x1, if it is the value of the derivative is greater than 0, it says that if x increases, the f2 also increases. This is what it means, right? If the whole value of this is greater than 0, right? Or if x decreases, if x2 is smaller than x1, then it means that f2 is also smaller than f1. If this is true, these two conditions are also true, right? If x increases, the value of the function also increases. If x decreases, let me just, it might not be, yeah, now it's visible. So what does it say? That if the whole conclusion till now is, if delta f by delta x is greater than 0, or the derivative of the function is 0, not 0, like if it is greater than 0, sorry, if delta f by delta x is greater than 0, then increasing the x means we are increasing the function value as well, and decreasing the x means we are decreasing the function value as well. Simple, right? Let me cover it up, then I'll explain you again. You'll better understand, believe me, I'll make you understand. And if delta f by delta x is smaller than 0, what does this mean? Let's say we find delta f by delta x, we tweak x, we record what is delta f for that tweaking, and we take up the ratio and it comes out to be smaller than 0. What does it mean? It means that if x increases, f decreases, right? Only that way it will be smaller than 0, right? If delta x is positive, delta f has to be negative. That will make the whole term negative. Or if x decreases, f increases. Otherwise minus minus will be cancelled out, right? If this term has to be smaller than 0, then these two conditions has to be true. Let me explain you in a neat way once more. Right now we have deduced two conclusions, that if delta f by delta x is greater than 0, it can be greater than 0, it can be smaller than 0. It means either this x increases, it will make f also to increase, right? Or if x decreases, the value of function will also decrease. Either of these two conditions has to be true. What is other case? If delta f by delta x is smaller than 0, what does it mean? That if x increases, f has to decrease, because if delta x is positive, delta f has to be negative. That only make the whole term, the whole ratio, that will give the whole ratio as a negative value, right? Or if x decreases, f increases, because that will make the whole ratio negative, right? Now let's think about this thing, right? I hope you guys are with me till now, right? Now, from the point where we started, what we wanted to reach at a value of x for which the function value has to be minimum, right? Now how we will reach at that particular point? Thing is that if let's say delta f by delta x is greater than 0, let's say we are at some point, like we picked up a random point and we compute the derivative, which is delta f by delta x actually, at that particular x that we pick up a value of x, we tweak that value of x, we record the delta f, corresponding delta f, we take up the ratio and we find that that is greater than 0, and we wanted to tweak x in such a way that we reach a value for which the function has to be minimum. How should we tweak the function? How we'll do that? Let's say if delta f by delta x is greater than 0, for that value of x, what we have to do? We have to reduce the value of x, right? To reduce f, because that will basically reduce f, we have to reduce the function value. That is our whole aim. The whole aim is to reduce the function value, and if at a certain point the value of the derivative is greater than 0, then we want to reduce x, because that will give us the reduction in function value. And if at some point the value of gradient is smaller than 0, then to reduce the function's value, we have to increase the value of x, because that will reduce the function value, right? And this whole story sums up and gives us the equation, this one: x dash is equals to x dash minus alpha time curl f by curl x, or df by dx, or delta f by delta x, anything you want to call it as. How? Because if let's say the value of let's try to understand it intuitively. Let's say we are at some point and this is at x dash, actually we are at some point x dash we find up df by dx and it is greater than 0, then what this whole equation will do, if this thing is positive and this is actually positive, alpha has to be greater than 0, small value 0.001 or something, alpha always has to be positive, you will set it yourself. Now if df by dx is, this whole term will be positive, right, and some positive value is getting reduced from x dash, so it will basically reduce the whole x dash, right, this one. This will happen if, according to this equation, if we update x according to this equation, then if this is true, if curl x by curl f by curl x is greater than 0, the whole x will come down if we update x in such a way. Or if df by dx is smaller than 0, sorry, I hope it is visible now. Okay, all right. So in like if curl f by curl x is smaller than 0, what does this equation will give us? This whole term will be positive, right, in that case, this whole term, because this will be negative according to this, and negative negative positive, a whole x will actually increase, right? So what does this equation say? That x dash is equals to x dash minus alpha time curl f by curl x. This equation says that you are updating x in such a way that it will reduce the whole function's value, right? If curl f by curl x is greater than 0, then it will reduce the value of x which is required, and if curl f by curl x is smaller than 0, it will increase the value, because negative negative will be positive, alpha is already positive, it will increase the value of x which is required, right? So basically what this equation tell us, that if you will update x according to this equation, the value of whole function will basically reduce, right? And what will happen if you reach that minimum point, at the point of minima? What is the characteristic of that point? The characteristic of that point is curl f by curl x will be equal to 0 at that point, if x is equals to local minima. If x is equals to local minima, this thing will go 0, and update in x will also go 0, right? There will be no update after that. Let's say we reach at a point where there is a minimum, then this gradient value, this one, will be equal to 0, and there will be no update in x dash. X dash will be same, will remain same after that, right? So this is the whole gradient descent algorithm, which is the iterative way of reaching to that local minima, right? So let me draw a clean visualization basically, but like this basically gives us the direction in which we have to move to reduce x. Let's say this is the function fx x, and we want what we want is, we want to find x at which fx is minimum. So what we'll do, we'll pick up a random x, let's say this one x0, we'll compute the gradient, and if it is, we'll keep on updating it according to this equation, x dash basically x minus alpha time df by dx. We'll find the df by dx at this point, we'll tweak up the x by little amount, will like there will be a corresponding tweak in f as well. We'll find the ratio, and if it is greater than 0, which will be in this case at this particular point, the gradient is 0 for this function, and here the gradient is negative basically. So this will be positive, so we have to reduce the x by some amount, and this alpha is actually the step size by which step size or the learning rate, you can call it as anything. Like it will give us the amount by which this whole thing will go in this direction. We'll update it, it will keep on going in this direction like this. If we keep on updating, it will keep on reducing and reducing and reducing. If we'll keep on updating it like this, ultimately it will reach at this point. At this point this value will be 0 because curl f by curl x is 0 at this point, and after that there will be no update, right? And if we start from here, like here the gradient value will be negative, so x has to increase. So it will keep on moving like this by small step size. That's why the step size has to be small, because otherwise it can directly jump from here to here, and then from here to here. It will keep on dangling like this. Like so that's why alpha has to be small. I hope you understood. Ultimately it will reach here, and again no update, right? So that is the whole gradient descent thing, guys. Like we have to find the direction of update by computing the gradient of the function at that point, and then we will keep on updating in that direction, and alpha step size or the learning rate has to be small, right? So that is the uh, whole DNA or whole blueprint of this gradient descent thing, guys. I hope you understood till now, the theory part at least. Now we'll jump into the coding part, then you'll understand more. So let's move in that part as well. So all right, now we are in the coding screen, and first of all we have to make the virtual environment. So I'm using UV to make the virtual environment. So basically you will learn UV init Python 3.12. UV is a very great package manager, guys, so I just suggest you to use the same. Our next command is UV init which okay, first of all I have to make the virtual environment. So UV venv Python 3.12. Basically it will install, like, make me the virtual environment with this particular Python version, and I have to activate its source dot venv bin activate. All right, we have finally activated our virtual environment. Let's select it here finally. All right, now we are good to go. Let me include the package uv add numpy, because that is important. Whole code I'll give you into the git directory. I'll share you the git directory basically. So let me import things. Import numpy as np. I don't know if we'll actually need it, but let's import it up. It's connecting. It's all right. So the first thing we need, what is the first thing? Like we have to, let's say we have a function first of all whose minima we want to see, function fx, which we talked about, and that is, let's say, return x square. Very basic example, right? So there's a function whose value we want to minimize. We'll start up with some random x, and we'll keep on updating that x according to gradient descent algorithm, and we'll see if we are able to reach up the local minimum. All right, so the next thing is we want to find, like, have a function which gives us the gradient of that function, this one. So it will be taking two parameters, the function name and x along with the learning rate, which is alpha, which it is giving us. Okay, the auto coding code thing is giving us correct thing. So basically we are doing the same, right? We are tweaking the x, and we are like this is the delta f and this is delta x. So this is correct gradient function, right? Next we have to choose random x. Let's say we take one random value, one this one, right? Now we have to have a function like which take this gradient descent, which runs up this gradient descent loop, which is okay, let me think of like I want to define it as a function which uh, gradient descent. Okay, auto coding thing is giving us correct results. Let's try to understand what it is. Like x init is the initial value, basically the function whose value we want to minimize, and learning rate, which we are keeping in our case, by which this thing has to be like this, the equation, right? We talked about x has to update according to this particular equation, x minus alpha time gradient of the function at that point, and gradient is this one coming up from here. So basically we are doing the same thing, and a number of iterations, like it is not keeping us, we are not keeping that while loop that we are running up it for some finite number of iterations, right? So that is also fine, that will give us the same results. Let's run it up. Let's test it up now. Gradient descent will pass up the function, and init init is actually this one. So let me keep it here. So it will give us basically the minima. So let me explain you the whole thing here, what is happening. Like this is the function we are taking whose value we want to minimize. This any random x we are choosing, and we are running the gradient descent loop for some finite number of iterations, and this is a gradient descent equation. This is the gradient function, which is this is the delta f, and this is the delta x, basically df by dx. This is actually the gradient, right? And this is the function. We can take any other, we'll test it for other functions as well, obviously. Let's run it up. So ideally it should give us a value nearby 0, right? Because at this value the things, the function is minimizing, right? It is x square, simple. Okay, so x minimum, okay, it is very small, right? It is close to 0, guys. So our gradient descent loop is working fine. So this is the gradient descent from scratch in Python, right? We can test it for some other function. Let's say we make it x 3x square, let's say, and we want to shift it to right, let's say. So it is not 3x square, but 3 plus x whole square, because it will make the global minima value to be -3. It should be -3, right? We run the gradient loop, or close to -3. We give it a random update, and let's run it up, and it is close to that value, right, guys? So our gradient descent loop is working fine, so our algorithm is working fine, basically. If you'll basically reduce the number of iteration, let's say you reduce it to 100 or 10, it will basically close to 3, not exactly 3. It is like having a wide difference. The number of iterations has to be large, guys, so that it can converge to that value. So it is converging fine. And this learning rate also has to be low, because if we increase it to 0.1, it might not be exact. Okay, it is in this case, but learning rate ideally has to be low, because otherwise it will keep on tangling in the way I explained you in the theory part. So all right, guys, I'll update this code into the Git repo, and I'll share the Git link into the comments below or in the description. Let's see. And I hope you enjoyed my video. We have learned the gradient descent from scratch. In future, I'll be bringing up more such basic machine learning courses, and we'll be doing some advanced projects as well. So please subscribe my channel and like my video if you find some value, if you understood something, because this is a very rare thing, as normally people learn big things and they just cannot answer very basic things into a machine learning interview. So this is a very basic thing. You need to know how to implement gradient descent from scratch, and we have done the same thing. And thank you so much for watching my video, and see you into the next one. Bye bye.